Hello, everyone. Welcome to the TTS SBc Client and Server Plugin demonstration. My name is Denisa Georgiana Vasile, and today I will introduce you to the newest plugin that allows you to test connections via the SBc AP protocol for the SBc interface between CBC and MME. In this demonstration, we will cover a few key topics. We will start with a brief overview of TTS and the SBc interface. Then I will walk you through the scenario we'll be demonstrating, using a sequence diagram to clearly illustrate the interaction between components. Finally, I will show you how to quickly create a scenario using a server and a client that communicates using the SBc AP protocol, making testing both simple and efficient. The most exciting part of this process is that it is designed for easy automation, saving you time and effort while ensuring reliable and repeatable testing every single time. Let's start by introducing the SBc interface using SBc AP. The SBc interface is the logical interface between the Mobility Management Entity, or MME, and the Cell Broadcast Center, or CBC. It defines the architecture used to transmit public warning messages in mobile networks. This interface operates using the SBc application part, or SBc AP, which is an application layer protocol that runs over the SBc interface. SBc AP specifies the message procedures and formats exchanged between the MME and CBC for delivering warning messages. The transport protocol used beneath is the Stream Control Transmission Protocol, or SCTP, which ensures reliable communication or multi-homing feature. In summary, the SBc interface is the connection path, while SBc AP is the set of rules and messages that flow through this path to manage and transmit public alerts. I would also like to highlight a powerful tool that some of you may already be familiar with: Top Testing Suite. TTS is a comprehensive suite of testing tools designed specifically for end-to-end testing, evaluation, and validation of telecom services. What sets this tool apart is that it's Java-based and combines the widely used JMeter platform with open-source components and specialized plugins developed by our systems. This combination results in a modular, multi-protocol, and multi-platform solution that can adapt to a wide range of telecom testing scenarios. Whether you need to simulate complex network conditions or validate service performance across different protocols, TTS provides the flexibility and robustness required for enhanced telecom service testing. Next, I will show you how the TTS SBc Client and Server plugins manages SBc AP messages through a simple sequence diagram. The main element in our sequence diagram is the SBc AP protocol, which establishes connection between the client and the server so that they can communicate with each other. On the right side of the diagram, we've added a server. For this demonstration, we'll be using a TTS SBc server element. On the left side of the diagram, we've added a client. This will be represented by two elements in the demo: the TTS SBc client and the TTS SBc timer, each representing one of the two scenarios we want to show. The first scenario involves the client making a request, with the server responding. The second scenario is reversed. As shown in the updated diagram, the client sends the message using the SBc AP protocol. After verification, the message is forwarded to the server. The purpose of the write-or-replace wording procedure is to overwrite the broadcast of the warning message. The server returns a write-or-replace warning response message using the SBc AP protocol. The client finally receives the response from the server. In the second scenario, the server initiates the write-replace warning indication procedure by sending a message using the SBc AP protocol. This message is forwarded to the client. Upon successful reception of the request, the client forwards the message to the server and returns a stop warning response. Now, let's see how the sequence diagram looks in the TTS. Before running the SBc elements from TTS for the first time, we recommend checking if your host is SCTP ready. It's essential to have SCTP enabled. Next, we'll build the server. We'll add a TTS SBc server configuration element and a new connection ID named server. We'll use 127.0.0.1 for the host and 123.6.8 for the port. For this demo, the multi-homing option will remain unchecked. Finally, we'll add a new thread group. Inside, we'll add two TTS SBc server samplers. The first one will be used for listening, while the second one will be responsible for responding to the client. We have the option to import a real pickup to use as our response. We can also add a function to verify specific variables. To do this, we navigate to the function helper, select the SBC server, choose SBC server, retrieve the port, and then click on Generate and Copy to Clipboard. Following this, we can paste it inside a TTS dummy sampler. As an additional step, we will add another TTS SBC server sampler to the thread group, which will represent the server in the second scenario. We will import the pickup here too and select the stop warning indication. This will represent the request sent by the server to the client. Now, let's shift our focus to preparing the client too. We will return here later to add more elements that will facilitate the testing. In the client script, we'll add a TTS SBc client configuration element. We'll create a new connection identifier named client. For the host, we will use the same 127.0.0.1, and for port number 123.68 as the server, leaving the multi-homing unchecked as well. We also need to set a timeout value for this connection. Next, we will add a new thread group. Inside this, we will need to add a TTS SBc client sampler. We will import our pickup to use as our request to be sent. We will also add a function here. As you can see, we have a comprehensive list of functions for both TTS SBc client and server plugins. Let's select the SBc client getRequestMessageName function and copy-paste it into the TTS dummy sampler. We will also need to insert a TTS SBc timer element into the thread group, representing the client. In the second scenario, we anticipate a stop warning indication message. We'll set the duration to 2000 milliseconds and ensure the response is not auto-generated. We'll import the pickup too, selecting the stop warning response to be sent by the client to the server. Back in the server script, we can add a TTS SBc assertion element to verify if the received message is as expected. We'll set the sample result to a 200 code. If the checkall element isn't crossed, the assertion stops at the first failed comparison element. Let's load the pickup file next. Please stand by while we add assertions to other elements from both GMX scripts. Now, we have imported script assertions, using both TTS SBc assertion and response assertion. The latter is mostly for the server that is listening, and for the functions, we will also need some listeners. We'll take this opportunity to introduce an often overlooked element, the TTS View Results Tree Listener, which is similar to the View Results Tree from JMeter. We'll also add the TTS SBc View Result and TTS SBc Message Listener. Before we start the script, let's initiate the pickup capture. The command is already prepared and will be used in the terminal. Now we can start both the server and client. Once both the client and server have successfully closed, let's also stop the pickup capture. We'll analyze it immediately. As you can see in the TTS View Result Tree Listener, all messages were sent successfully. Now, let's proceed to check the SBC-specific listener. First, we have the TTS SBc View Result. This allows for inspection of sent commands and received responses, which is particularly useful for functional testing and building documentation. It enables viewing of messages in 3XML and formatted form, ready to be copied and pasted into documents. It also allows for viewing of assertions. Second, we have the TTS SBc Message Listener. This listener can be used to inspect any exchange of SBC messages. This includes the SBC AP elementary procedure, such as write, replace warning request, replace warning response, and so on. Let's now examine an unsuccessful assertion. We can go to the client and manually modify the value of sequence 1. After saving and running again, we'll see in the TTS View Results tree that the assertion on the server has failed, as expected. The TTS SBc assertion failed due to a discrepancy between the expected value of 4352 and the actual value of 4359. Let's delve into the pickup capture taken earlier. Our first step is to decode the traffic by specifying the correct port number used in our client-server connection. We'll adjust the port value to 12368, which corresponds to this connection. Next, we'll ensure that the appropriate dissector, in this case, the SBc AP protocol dissector, is selected to interpret the packets on that port. After this, we'll apply a display filter for SBc AP to isolate only the packets related to this protocol. Once filtered, the messages exchanged between the client and server become clearly visible. Here we can see the write replace warning request representing the client, followed by the write replace warning response signifying the server. Then we have the stop warning indication, which represents the server's request, and finally, the stop warning response, which is the response received by the server from the timer. That brings us to the end of our demonstration. We've set up the server and client, used real PCAPs to send messages, and employed TTS SBc sessions to ensure message accuracy. We monitored results with TTS SBc listeners and reviewed the pickup in Wireshark to see all messages clearly. This demo provides a comprehensive guide on setting up testing SBc interface communication between MME and CBC with TTS. Thank you.